Alright guys, welcome back to some more Mastering Physics. This is chapter 7, and I thought we should be going with question number 15 because I thought this was the hardest question to homework, and I thought the homework this weekend was pretty tough actually, harder than usual. So let's get right into it. So we're given an electron in a cathode-ray tube is accelerated for a potential difference of 10 kilovolts, then passes through the distance d equals 1.7 centimeter wide region of a uniform magnetic field in this figure right here. And it's the question is asking us what field strength would deflect the electron by 9 degrees. I don't know why that looks like that, but that's actually faded, just copied over wrong, I guess. So we're going to label what we have. We're given a distance of 1.7, and that's actually, let's convert that to meters so our units are consistent. So that'll just be 0.017 meters. And then, if you guys don't really understand the problem, which I didn't really to begin with, is that if this is the electron right here, it's traveling right through this cathode ray tube, giving it some velocity, and then it enters this magnetic field of this distance. That's how wide it is. And instead of having it come straight out the other side, we want the electron to deflect a little bit by 9 degrees in this case. So it comes out a little bit down instead of straight out, right? So that's what's basically the problem telling us, and we want to find a magnetic field that would make this happen. So the equation that will make this happen, right, we need to know is our cyclotron, right? The radius of a cyclotron is equal to the mass times the velocity, right? That's the velocity, not the volt or anything like that, not the electric field, time divided by the charge, right, times it by B, which is what we're trying, the magnetic field. So obviously we're not trying to find the radius of an electron, but we do need to find it to solve for B. So let's go ahead and rearrange this equation to solve for B. B is equal to the mass stays up top, so there's the velocity divided by charge stays, but we just need to divide a cyclotron back over, so okay. Now we have everything, right? No, but we don't have the velocity or the radius of a cyclotron. But I'm going to box this in. This is the equation we're going to be using. It's a terrible box. But we're going to be using the mass and the charge of an electron because that's what's going through all this stuff, right? The electron. So the mass of an electron is equal to 9.11 times 10 to the negative 31 kilograms. You can do a quick Google search of this, and that's what I did. Or it's probably in the book somewhere if you don't want to take my word for it, right? And the charge of electron, that is 1.6 times 10 to negative 19, I believe. That should be correct. We'll see if we get this answer. The answer is up here, guys, so if you don't believe me, that's what it is. And let's go ahead. Velocity, we'll find that later. I want to start with the cyclotron with this picture right here. So you guys might be wondering, what's the cyclotron, right? So if we're deflecting this electron down, right, we deflect it, we're putting a force on it, it's going to start spinning off control, and it's going to be going in like a circular shape or something, some sorts. And if we want to find the radius of this cyclotron, this is the cyclotron, this circle thing, we want to find the radius, this is the radius, right? That's a terrible line. I'm just trying to draw a line here. That's R for the radius of the cyclotron, which is what we need. And then to keep things straight, let's put another one right here too. Because I guess the dot's actually right there, right? That's R as well. So if we know that this is 9 degrees, all right, if we know that's 9 degrees, we'll go ahead and fix that. We can go ahead and find this angle, all right? Because if that's a right angle, like this picture is just a little bit weird, but just think about it like this: if this line wasn't here, that was right there, okay, and this line is tangential to it, and that's 9 degrees. We can call this like some type of radius right there. Yeah, that could be our radius line. We can find this angle right here, right? Because that'll just be 90 minus 9. And 90 minus 9, that is just, trying to draw these lines straight. That's 81 degrees. And then if this was to be a right triangle, then we can find this angle right here. But I don't want to confuse you guys. This line is actually going to be right here, right up against the wall. It's just that this line is a little bit messed up, okay? So, bam. That's just a really tight angle. Alright, that's 9 degrees right there. That's what they're giving us. And that's 81 degrees because this is a right triangle. And we can find this angle just by taking 180 minus 81 minus 90. So that's going to be 9 degrees again. So I'll write it right here. So this angle right here, right, this is going to be a 180 minus 81 right there, minus this right angle. And then it's going to be 9 degrees. That's how we get that. But how do we solve for R? We don't know this. We don't know any of these lengths. Let me just go ahead and redraw this triangle, right? If we redraw this triangle, okay, that's a terrible redraw. If I redraw this triangle, okay, I can't simply redraw this triangle. But if we successfully redraw this triangle, we know this angle, right? That's 9 degrees. We can just cut it off, right? Cut it off short right there. Forget about that nonsense up there. We know this distance right here. This distance is D, 0.017 meters. That's R, and that's R. And we can solve for whichever one we like. So let's go ahead and use sine, right? Because we got opposite over adjacent, or we can use tangent as well. But let's go ahead and use sine. So we get sine of 9 degrees is equal to opposite, which is 0.017 meters, divided by the hypotenuse. And so let's just solve for R. So we multiply both sides by R, divide both sides by sine 9. So R is equal to 0.017 divided by sine of 9 degrees. So R, if I type this in the calculator, that is going to give me 0.1087, yeah, something like that, meters. So now we got the radius of a cyclotron. 1, 2, 3, and the only thing we don't know is the velocity. Now this is where we got to use the conservation of energy. So if you guys remember, the conservation of energy was the final equals the initial energy, right? So E final equals E initial. And we know, let's go just write it out, you know, the final. So it's just going to be 1/2 mv squared plus the potential. Let's just put F for final. Potential, that'll just be the charge times potential difference is equal to 1/2 mv squared initial plus Q to V. So this is just potential, so that's kinetic and potential. So this is final and that's initial as well. Initially, we don't have any kinetic energy because it's accelerated towards the right for a uniform magnetic field, so the velocity is going to be 0 initially from this point, right? So this all goes to 0. And then initially, the change in potential energy is going to be 0 as well, because there is or not change in potential energy, because there's no delta V in the initial stage, because it's just 0, right? 0. So that goes away. So all we're left with is really just 1/2 mv squared final, which is what we're trying to find. Vf is equal to if we just move the center side, minus Q delta Vf. So now we can go ahead and rearrange a bunch of stuff and solve for Vf. So if I multiply both sides by 2 and divide by m, I will get V. I'm just gonna, okay, well, you guys know this is the velocity, right? I'm just gonna leave it as a V. I don't want to write that every time. This is gonna be -2 Q change in V. That's not velocity. And we divide it by the mass, and we take the square root of that. Right, that looks pretty good. So now let's go and plug in some numbers. We got the square root of -2. Charge of an electron is 1.6 times 10 to the negative 19 coulombs. And then we have the delta V, which is just the change in velocity. So the change in velocity, it's going to be 10, right? Because 10 minus 0 right here. So 10 minus 0 is going to be 10, but that's kilovolts. So we got it's actually 10,000 volts. I'll divide the mass of electrons. So that is 9, I almost wrote 8. 9.11 times 10 to the negative 31 kilograms. So if you guys derive what volt is and then kilograms, you guys can figure it out. This will give you actually meters per second. So if I type this on the calculator, if you give me a 1 second real quick. Oh, by the way, the charge of an electron is actually negative, so that will make, if you guys think, well, we can't take the square root of negative, but the charge of an electron is negative, so that will do away with that issue. I actually tried to square root this with a negative. I feel pretty bad. Okay, but that will give us some big number. I'm sorry it took so long, but that gave us 5, 9, 2, 6, 7, 3, 8, 9.77 meters per second. This does cancel out because the volt is, I forgot what it was off the top of my head, but it does cancel out. If you guys try to look up the how these units are derived, it does come out to be meters per second. So that is the velocity. And now we have the radius and the velocity. Let's go ahead and plug everything into this main equation, right? So B is equal to the mass of an electron, again, that is 9.11 times 10 to the negative 31 kg. And then we have the velocity, which is what we found right there. Geez, I gotta rate this 267,389.77 meters per second divided by the charge of an electron, which is just 0.6 times 10 to the negative 19 coulombs, and we have the radius, I believe, which is just 0.109 meters. Notice that we kept everything in the big units, right? No centa, kilo, none of that stuff. So if we plug this into our calculator, you guys bear with me for a second. Scroll up to find the answer. Alright. You guys should get well, if you guys had the same number, the same problem I do, 0.0031, and that would just be Tesla. And that's it, how you do this problem. It's a long one, but hopefully this helped. Thanks, guys.